Now let's talk about work. Work is said to be done when a force acts upon an object to cause a displacement of the object in the direction of the force. The SI unit of work is joule. Work is equal to force times displacement.
Power. In a simple term, power is the rate at which work is done. The SI unit of power is watts. Mathematically, P is equal to W over T. Let's term this as equation 1, where P is power, W is work done, and T is time. We can derive other equations from equation 1. We know W is equal to F times S. Work done is product of force times displacement. So let's put this into equation 1 to obtain P is equal to F times S over T. From the concept of motion, velocity is equal to displacement over time. From equation 2 and 3, we can write that power is equal to force times velocity. Dimension for power. Power is given as work done over time taken. So the dimension for power is equal to the dimension for work done over dimension of time. Since work is the same as force times displacement, we can also write this dimension for force times dimension of displacement over dimension of time. Since force is equal to mass times acceleration, we can further write that the dimension for power is equal to dimension for mass times dimension of acceleration times dimension of displacement all over dimension of time. So we know dimension for mass is m, and dimension for acceleration is lt exponent minus 2, and that for distance is l, all over time. Now, by the concept of indices, let's further simplify. So when we simplify, we will get a dimension for power to be equal to ml square t exponent minus 2 all over t, and this further gives us ml square t exponent minus 3.
Let us now solve some questions. Which of the following units is equivalent to the watt? So we saw earlier that the dimension for power is equal to mass times length squared times time exponent negative 3. We now substitute the basic units for each of them. So for mass we have kilogram, then for length squared we have meters squared, then for t exponent negative 3 we have s exponent negative 3. So this is equivalent to the watt. Hence the correct answer is B. We have another one here. The total area under a force velocity graph represents, so that area under the graph what will it represent? Is it energy, momentum, power, or pressure? So let's see. We have our graph over here. We have velocity against force. So the area under this graph, what would it represent? So we know this is a triangular region. So this is an instance that we have taken, and we know that the area of this triangle is given by half times base times height. Half times base times height. So we know the base now is velocity and the height is force, so we get half Vf. But we know that multiplication is commutative, so we can rewrite this as half of V of F times V. So what next? We do some substitution for the velocity to obtain F times displacement over time, because we know velocity is equal to displacement over time. Now we know that the product of force times displacement, the product of force and displacement is work, so that will give us work over time. Then work over time is power, so this is equal to power, and half of power is the same power. Scalar times power is still power. Therefore the area is power. Area under the force velocity graph is power. A body is pulled through a distance of 500 meters by a force of 20 Newton. If the power developed is 0.4 kilowatt, calculate the time for which the force acts. So we are going to calculate for the time for which the force acts. We have some information from the question. We were given that the distance covered is 500 meters. Then we also have that the force is 20 newtons. Then we also have that the power developed is 0.4 kilowatt. 0.4 kilowatt. So note that in this case power is given in kilowatt, so we need to do some conversion. But before that, let's see what we are looking for. We are trying to calculate for the time. We are calculating for the time. So what is the time for which the force acts? The time for which the force acts. Now we know that work is the product of force times the displacement. So let's calculate for the work first. So work is equal to force times displacement, and this is equal to force is 20 newtons times the displacement, which is 500 meters, or the distance, which is 500 meters. And when we calculate that, we obtain 1000 joules for the work. Then again, we also know that there's a relationship between work, time, and power, and we have all this now. So we know power is equal to work over time. So this means that we can calculate for the time over here. But before that, let us convert the power, which is given in kilowatts, into watts. So that will be power will be equal to 0.4 times 1000 watts, because 1000 watts gives a kilowatt. So power will now be equal to 0.4 times 1000, and that is equal to 400 watts. 400 watts. Now we know power now in watts, and we also know work in joules. So we can now solve for T and do our substitutions. So we know T will be equal to W over P, which is work over power. So the work is 1000. The work is 1000 joules over power, which is 400 watts. So 1000 over 400, we need to simplify 1000 over 400, and that will give us 25.0 seconds. Now let's take this example on work. Using the force displacement diagram shown above, calculate the work done. So this is the force displacement diagram, and we want to calculate the work done. So the work done is simply equal to the area under the displacement force graph, or force displacement graph. So we need to find the area of this triangle to calculate the work done, which is half base times height. Half base times height. The base is 20 units and the height is 100 units. Therefore, the work done will be equal to half of 20 times 100 times 100 joules. And we know that half of 20 is 10. Then 10 times 100 will be equal to 1000 joules. Therefore, the work done is 1000 joules. Hence, the correct answer is option B.